whatever I write on, the main thing. And if that stops bouncing, that's bad, because that means my audio's gone.
Forgive me if I told you I don't have my contacts.
Uh-oh. I choose you.
I just can't see right now.
I hear you. I just took a road trip without taking my glasses, so if I stick it here, can you see it?
Mm-hmm.
Is it in your way?
No.
Okay. All right. Let us begin then. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you again for these students, and I just pray that you'd bless our work today, Lord. We thank you for all your many blessings to us and this creation that you have made for us to enjoy. Help us to enjoy the math today and just to serve you in doing it, Lord. In your name I pray. Amen. So, let's see here. You guys have top hatted, I'm assuming? Well, some of you have. Don't wait too long. At some point this thing will like sleep. So, oh, is my marker sad? The marker is sad. 8, 4, 9, 3. All right. So, a couple of points of order I should make. I noticed that my email in the My Labs was actually set on my previous school's email, so I haven't been getting your messages. Like if you did any messaging within the My Labs, I wouldn't get it. So like, I tell you guys, email me if you have a problem. I really meant that. If you hit like help me contact your instructor through the homework system, it wouldn't have contacted me up till now. Now I did change my email, so I think it will work now. It should forward your message to my Liberty email, so I should see it. All right. If in doubt about whether or not the homework system has actually sent me an email, just email me directly. All right. So I do intend to answer your questions through email when you have them. But of course, we do have in-person class, so you can bring your questions here. Even better. That way, if I answer it, everybody gets to see the answer, right? So, so that's the one thing. The other thing is, I'm still figuring out exactly how grades sync between My Labs and Canvas. If you have grades in My Lab, those are real, right? And they will eventually transfer to Canvas. I wouldn't worry too much if it's not in Canvas yet. Now, if at the end, if we get midway through the course and your first 6 homeworks still haven't transferred through, then I'm probably going to notice that and figure out what's going on. I have hit the grade sync button, so I'm pretty sure all of the grades from homeworks like 1 and 2 should be transferred over to Canvas. All right. But just saying, because some of you have had questions about that, so I thought I should address it. Any questions about anything else going forward? Yes, sir.
Can I ask a question about one of the homework problems?
Which homework problem? Sure.
The one with the rectangle and
I will say, if it's one of the ones I've already solved in class, I'm probably not going to work it again. But which homework with the rectangle?
like question 29.
See, I think 29 I worked in class, didn't I? What was your question about it?
It was supposed to be like, do you want to parentheses when doing the work?
Parentheses when doing the work.
Like 28 or minus 2x or something?
Here, I found it. So your question is about like the format of the answer? So if it's in a quiz or something in class, then if you do the work correctly, I will adjust for that, right? It wanted the answers as like, so for mine, not my number 29, it works out to like 17 and 11. So they wanted the answer as like 17, 11. But there's another problem in your homework which has like a separate box for length and width, right? I mean, so it's a question of how they set up the homework. Yeah. Uh-huh. Completely reasonable question. Other questions? I can't say that there are no stupid questions because I have asked stupid questions before, so I have data to the contrary, But, but most questions are not stupid. I will say that. Okay, so let's talk about inequalities. All right. So you guys, so inequalities and interval notation. I talked a little bit about interval notation, right? But now we need to get into it. So let's just go through the basic rules for inequalities. So here's some properties. A less than or equal to B is equivalent to what? You could trade that for B greater than or equal to A, right? That's one thing you can do. You can flip inequalities like so, right? Another thing we can do, if we have a positive number, right? And we have A less than or equal to B, well, that implies that CA is less than or equal to CB. So if we have a positive number, we can multiply an inequality and maintain the direction of it, right? However, this is the thing that gets people. If C is less than 0, then what? If we have A less than or equal to B, that implies that CA is greater than or equal to CB. So multiplying an inequality by a negative, it flips the inequality over, right? So these are the big ones. There are others. You can add numbers across an inequality, right? Like, for example, if I have, x is less than or equal to y, then that implies that x plus a constant is less than or equal to y plus a constant, right? This is also true. Anything else you guys can think of? Fractions are kind of funny, right? Like if we have 0 is less than A is less than B, what does that say about the reciprocal of A and B? So basically you can take this, right? And you can multiply it by 1 over A. What happens? We get 1 over A times A is less than 1 over A times B. Now how do I know that I can multiply it without changing the inequality? Because I'm assuming that A and B are positive, right? So that means that 1 over A is also positive. So this gives me 1 is less than B over A, right? And then we can do what? We could divide the inequality by B, right? We can multiply by 1 over B. And that would give us 1 over B is less than 1 over B times B over A, which is equal to what? Just 1 over A, right? So let me just take this whole discussion here, make it a thought bubble, right? This implies, what about the fractions? It implies that 1 over B is less than 1 over A. Now sometimes students are like, what? How can that be true? It's much easier if you just think about it in terms of numbers, right? Think about this, like is 3 less than 5? Well, surely it is, right? How about a third and a fifth? Which comes first? Right? So the smaller we make the denominator, the larger the fraction, right? The larger we make the denominator, the smaller the fraction. Does this make sense? Hopefully I said what I thought. Every so often I say something like this out in words, and I flip the word larger and smaller, and then it ruins the meaning, So if I do that, you call me on it, yeah? Any questions? All right, let's start working some problems. Then the other thing we have to talk about is the number line and interval notation, right? So how about this? If I have x is less than 6, all right, let's picture the solution set using the number line. So the number line, I'll draw like this, yeah? And let's put 6, let's see here, somewhere, right? And I'm going to do it that way because I'm thinking about it. X is to the left, right? It could be over here, for example. And so to picture this, the solution set I've drawn in red here, the solution set to x less than 6 is what's called array, right? This is an array. Sometimes it's called array. It's also known as, so solution set is equal to minus infinity to 6, right? So the solution to an inequality is typically expressed using interval notation, right? So we have 3 different ways of looking at this. X less than 6, the number line picture, right? And usually in your book it's got like hash marks and it's got a bunch of numbers here, like I should put a 6 here, right? And typically there's like a 7 and a 8 and so forth, you know, blah, 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 blah. All right, so this is the solution to that inequality, interval notation. Let me do something that's a little bit more, let's say, nuanced. Example 2. What if we were trying to find the solution set to 3x plus 8, which is between, let's say, 2 and minus 4? So minus 4 less than 3x plus 8 less than 2. Let's solve this inequality. All right. First, I'm going to try to solve it first just by isolating x. And second, I'm going to make a picture of it in the number line. And then third, I'm going to tell you what the interval is that's the solution here. So can you guys tell me what I should do first to isolate 3x? Yep.
Do you subtract the 8 to both sides?
Subtract 8 across the inequality, right? So if I subtract 8 from both sides, so minus 8, minus 8, minus 8, all across, right? We get minus 12 is less than 3x is less than minus 6. All right? Then what? Divide by 3. We get minus 12 over 3 is less than 3x over 3 is less than minus 6 over 3. Wow, this thing worked out the whole numbers. Wow, talk about my good fortune. I just made this problem up. I mean, I prepared it before class with meticulous care and detail because the numbers we put here really, no, I just made it up. The fact that this is whole numbers is amazing. We're very lucky. So minus 4 is less than x is less than minus 2.
I wish I was more enthusiastic about math.
I'm just enthusiastic about happy accidents. That's a happy accident. Okay, so anyway, there, in one school of thought, that's a solution, all right? That describes it, yep.
I just have a question. I might be wrong, but let's say it was a minus 3 that you needed to divide by and not just the 3. Does the symbol change, like switch sides, or does it stay the same? Because I feel like I remember something like that. Where it needs to switch if you divide with minus, but I'm not sure if I remember correctly. Sure.
Let's see here. So this is less than or equal to, say, 1 minus 3x less than or equal to 27. We'll do that for our next. We'll see that question. We'll see that next. Okay. But you're right. It would flip if there was a minus. So we'll see that over there. And I better add an x over here. This will be our next example. Let me finish this one. So this, what I've written in blue, is one way to look at the answer. But you're exactly right. It's because we divided by a positive number that we didn't flip the inequality. Now, we can picture this in terms of the number line, right? So maybe this is minus 5, minus 4, 3, zeros over here. So where would x be, potentially? It could be, at like -3-ish, right? X could be here. But it's got to be between -4 and 2, right? And then we draw like this to indicate that -4 and -2 are not included. All right? And also, once you draw that picture on the number line, it suggests what the interval notation solution is here. So solution set is equal to -4 to -2. And this one. So far, so good? Yeah, go for it.
If -4 and -2 were included, how would you write that out?
So if instead of having strict less than in both places, if we had less than or equal to, then we put like a square bracket at the end. Listen, there are really two dominant notations. Some people use like this and this for including the endpoints. This book that we're using uses this to include the endpoints. The other popular picture for excluding the endpoints is to use open circles. Your book uses like this to exclude the endpoints. So
Do you want us to use what the book uses? Or?
you could use either system of notation if you wanted to. I wouldn't be much bothered either way. Don't write your intervals as the French, though. That I can't tolerate. Do you know how the French write their intervals? And if you have like a French upbringing? So the French will write something like 0, 1 as, so it's like the other way. The brackets don't include them, so they're facing outwards. They just do the square brackets like that instead. But like I said, this is forbidden. Sorry, French people. Well, French mathematicians, really. I don't know about the French people. They might not care either. The French people may care as much about math as most American people. So I don't know. We'll see. I've never been to France. I haven't really talked to a lot of Frenchmen, so I really can't say, you know. You guys have a lot of experience with the French? No? All right. No. Then we'll have to stay in the dark, I guess. How about this one? Now this one is a little bit funnier, see, because we've got x's here and here. So like the first thing I would want to do is to isolate x. If I subtract x across the entire thing, right? We can do that. Whether x is positive or negative, you can add or subtract it, right? Addition and subtraction across inequalities don't mess with the inequality, right? Multiplication and division, that's what you got to watch out for. So we get 3 is less than or equal to 1 minus 4x is less than or equal to 27. Now what should I do? I said, you heard of subtract 1? I like that. Subtract 1 across the inequality. We get 2 less than or equal to minus 4x less than or equal to 26. Now we can divide by minus 4, right? Dividing by minus 4 is the same as multiplying by minus 1/4, right? Dividing is multiplying by the reciprocal. So let's divide by minus 4. And what's going to happen to us when we do that? So am I right or am I wrong? Why am I wrong? Right, we have to flip the inequalities. When we do we divide or multiply by a negative number, the inequalities flip. Right? So this is what? Minus 1/2 greater than or equal to x greater than or equal to 13/2. So I don't like this as a way of presenting the answer. To me, it's better. better flow if we do minus 13 halves, less than or equal to x, less than or equal to minus 1 half. So I'm just going to take the inequality and restate it in terms of less than or equal to rather than greater than or equal to, because now there's a natural flow to the number line solution. The number line solution looks like, let's see here, we got like minus 7, and over here I got 0. So basically it's like so, from minus 13 over 2 to minus 1 half, right? 13 over 2 is, by the way, minus 6.5, right? So it's something like this. Sorry, my color coding is, you can't see the contrast of purple on purple, can you? I'll switch it up here. There we go. That's the picture. Something like that is a picture of the number line or the solution set to this inequality, right? By the way, this is a compound inequality, right? Because it's actually two equalities all at once, right? So x would be somewhere in here, typically. What's the interval? The interval here, the solution set, we got minus 13 over 2 to minus 1 half. There you go. That's the solution set in interval notation. Oof. Goodness. Don't try to drink coffee. It's not a good idea. Okay, let's see if I can find another one here. Example 4. We might face something like 5x plus 7 over minus 2 is less than or equal to 3x plus 5. How would we solve this guy? And this time I'm just going to give my answer in interval notation, okay? I guess the first thing I would do here, I'd multiply by minus 2 because the minus 2 is offending me, So multiply by minus 2, what's that give us? We get 5x plus 7. Now, careful, since we're multiplying by a negative number, we have to flip that to greater than or equal to minus 2 times 3x plus 5, right? Not just for division.
With negatives.
Yeah, we flip the negative when we multiply or divide an inequality by a negative number, either one. We have to flip it. And, okay, so let me distribute over here. We got minus 6x minus 10, right? And then, so let me just rewrite it one more step down here. I'm just going to clean it up. 5x plus 7, I'm just rewriting what I already wrote, greater than or equal to minus 6x minus 10. What do you want to do now? Add 10. I mean, we could do that. And then do what? Subtract 5 and add 10? All right, well, I'll do it. So 5x plus 10. 5x plus 10. Now that will get me, the 5x's cancel, we get 17 greater than or equal to, looks like minus 11x. Now what do we need to do? Divide by negative 11, right? That's going to do what? Yeah, it's going to flip it back. So we get minus 17 over 11 is less than or equal to x. Again, okay, so then what does that mean the answer is? So we're looking at our solution set. it's equal to x in the reals such that minus 17 over 11 is less than or equal to x. Or you could say such that x is greater than or equal to minus 17 over 11. Now that is not interval notation yet. This is so-called set builder notation. This means element of. This is read such that. Now, this is the real number system. So like this is the same as this guy. My handwriting is degrading here for some reason. Let me try that again. Eventually I'll get it like I like it. Anyway, so what's this in an interval? We have minus 17 over 11 and then infinity. X is greater than or equal to minus 17 over 11. Any questions? All right. So all of the ones we've been doing so far are what I would call linear inequalities. Right? So linear inequalities allow you to just simply apply the basic rules of inequalities step by step, isolate x, that's your solution, right? But there are other inequalities we need to solve which are not linear, right? Which really require other techniques, okay? So let's talk about those. So what I'm going to do is I'm going to proceed by solving. I'm going to show you the method, all right? So here's example 5. Are we over? Did you move the camera over here? Yeah. Okay. Cool. Thank you. So suppose we've got x squared minus 3x plus 2, right? And we're looking for that to be greater than 0. So this is an example of a nonlinear inequality. The way to solve these is to factor it, all right? Find the places where it's 0. Make a number line to express where it's positive and negative. And from that, we'll read the answer. So step number 1, we factor. This is x minus 1 times x minus 2, right? So the zeros of the expression are what? X equals 1 and 2. So I make a number line, like so, and I put 1 here, and I put 2 here. And then I have to test a point in each subregion, right? Okay, so you draw a number line, plot the zeros, and then test point in each sub-interval. All right. How do you test a point in each subinterval? You just have to, let me start us out. Over here is 0, right? What's that?
The one that you just underlined, what does that say?
Test?
Test? I'm sorry.
Sorry, yeah, I shouldn't try to write at this level. So I'm saying test point in each subinterval. Let's say each case. There we go. There are 3 cases here. You're either to the left of 1, you're between 1 and 2, or you're to the right of 2. Those are your cases. 0 is to the left of 1. Plug 0 in, what happens? I put in 0, I get 2, right? Plug in 0 into the expression, I get 2. So I put pluses here. I put 4 pluses, you could put 5, you could put 2, it doesn't really matter. It's an illustration, right? This is a mnemonic tool to help us understand what's going on. How about between 1 and 2? What's a good test point there? 1.5? Is that correct, guys? So the answer to that is there is no correct test point, which whatever you pick, as long as it's actually in that case, right? 1.5 is a good choice. If you plug 1.5 into the expression, what do you get? 1.5 minus 1 is what? 0.5. 1.5 minus 2 is minus 0.5. So we've got plus times minus, which is minus. So in between 1 and 2, the expression is negative. All right. How about past 2? What's a good test point past 2? 3. Some of you might say 2.5. Which one of you is correct? It's kind of like when I asked my 5-year-old which was better, at the house we were visiting this weekend or Grandma's house. He rejected my question and said that they were both good. But he's a wise 5-year-old. He realized the trap. So 3 is a good point. Plug in 3. 3 minus 1 is 2. 3 minus 2 is 1. 2 times 1, positive, right? Plus, plus, plus. Pluses. Once you draw this number line for a given expression, it unlocks all questions about the inequalities for that question. With this number line, I can solve the question asked easily. What's the solution? So we're in the read-off answer phase. All right. From this, where is it positive? Solution set. We can do minus infinity to 1, unioned with 2 to infinity. This is union. Remember how we define union of sets? A union B is X such that X is an element of A, or X is an element of B.
So they intersect.
What's that?
When they intersect then?
They do not intersect. No. There is a gulf between these two from 1 to 2. All the real numbers between 1 and 2 make the expression negative. Those are not in the solution set. Example 6, if you wanted x squared minus 3x plus 2 less than or equal to 0, solution is 1 to 2 included. By the work we already did for example 5. Why do I include the endpoints? Because the endpoints make this expression 0, right? And if we're solving less than or equal to 0, we have to include the endpoints as well, because that's what makes it 0. Is good? Is no good. Now some of you will be able to do this without the number line. But almost none of you will be able to do the following problem without the number line, idea. Now some of you may have been taught to make a table before and to put different factors and make like a grids of pluses and minuses and organize your work that way. And if you were taught that way and you remember it and you still want to do it that way, more power to you. but I don't teach that way. So, all right, so example, where are we? 7? What if we came up against something like x squared minus 5x minus 6, all right, divided by, let's say x squared minus 9. And we want to figure out where this is greater than or equal to 0. Excuse me. So the idea of example 5 is basically just this. The places where it can change from plus to minus have to be at zeros. Here we're using an insight kind of from, well, perhaps it's from calculus, I don't know. But essentially, if you've had experience before graphing, you know that the places where the polynomial can change from plus to minus are places where it's 0, right? Or they're places where what? There's like division by 0 that we'll learn later that corresponds to like a vertical asymptote, right? So vertical asymptotes can go from like infinity on one side to minus infinity on the other. That's a place where it could switch signs. So when you're thinking about whether that expression is positive or negative, you really need to keep track of places where the denominator could be 0 or places where the numerator could be 0, right? Those are going to be what I would call algebraic critical points. So our goal is to find all zeros of numerator and denominator. So let's see here. X squared minus 5x minus 6 is factors how? X squared minus 9 factors how? Can you guys factor these? X minus 6, x plus 1, right? This is just x minus, or x plus 3, x minus 3, right? So what are the zeros? Zeros include, we've got ourselves a 6, a minus 1, a minus 3, and a 3. Remember, you have to flip the sign of the factor to make the factor 0, right? Like, you got an x plus 1 here. How can that be 0? That's 0 when x is equal to minus 1. That's why I have a minus 1 here and not a 1, right? Be careful of that. Now you got to put them in order in the number line. Which comes first? Which comes last? Yeah, say, we had 6. 6 is last. Then what? 3. Okay. -1. Okay. And by the way, is my number line to scale? Probably not. I don't care about that. They just have to be in order. All right. And now we need to do some test points to figure out whether the expression's positive or negative in each case. So, all right. Let me tell you a trick. So we just figured out this is x minus 6 times x plus 1 over x plus 3 times x minus 3. Right? We're trying to find where that's greater than or equal to 0. So observation. All factors appear at odd power 1. There's a theorem, essentially, that when you have an odd power of the factor, you're going to flip from plus to minus as you go across the 0. So what that means is that every time we hit a 0 here, we're flipping from positive to negative. So I don't need to test 1, 2, 3, 4, 5 test points. I just need to test one, and then I can propagate out from there. The easiest test point is always 0, if you got it, right? How about zeros here, right? Plug in 0, what do you get? 6 minus 6 over minus 9, which is minus over minus, which is plus. So we get pluses up in here. All right? Then, using my theorem, trick, whatever you want to call it, trick, signs flip for odd factors. Sorry if you can't see that. Can you guys, did the green show up for you guys? I don't know. It depends on the glare of the window in here. So that means this is minuses, this is minuses, and this is pluses. And that's pluses. Now you could try some other test points just to check on it, right? If you want. Like we could try plugging in, just for kicks. Let's try to plug in 7, see if it works, yeah? If you plug in 7, what happens? You get 7 minus 6 is 1, 7 plus 1 is 8, 7 plus 3 is 10, 7 minus 3 is 4. They're all positive. If you have a fraction of positive things, it's positive. Hooray, it worked. Okay, so what's the solution then? We're looking for greater than or equal to 0. So I wanted to do it interval notation, my bad. So how about minus infinity to minus 3, all right, union with minus 1 to 3, union, I'm leaving some blanks in here, 6 to infinity. All right. So guys, do we include or exclude these points? Logically, let's think through it. Minus 3, do we need to include it or exclude it? Is it in? Is it out? What happens at minus 3? It's a 0, but what kind of 0 is it? See where it's coming from? Minus 3 is a division by 0. That is not in the solution set. We cannot divide by 0. So minus 3 we must exclude. Graphically speaking, in a couple weeks, that corresponds to a vertical asymptote. Okay? Minus 1. How about that one? We can include that one. No harm, no foul. Minus 1 is coming from the numerator, which can be 0. That's perfectly fine. And notice that we're solving greater than or equal to 0. So we're looking for equals to 0 in our solution set, right? 3, include or exclude? We've got to exclude. It's got division by 0 again, because plug in 3, we get division by 0. So we exclude 3. What about 6? I heard include, right, because we get 0 in the numerator, which is fine. So there you go. If you tried to solve this inequality, not using the number line method, your logic would have to break up into 3 disjoint cases, right? There's a relatively small number of students who are able to hack the logic in this kind of problem. But number line lays it all out for us, just like that. Yep. I see you have a question. It's below the surface, but it's coming. No? No?
I was just wondering how we get like zeros from like the denominators.
Oh, I factored the denominator. So my question is, what will make the denominator 0? Right? So I just factor the denominator. That tells me where it is. What if you couldn't factor the denominator? Then what would you do? I guess then you'd be in trouble. I don't know. I mean, honestly, in real world problems, sometimes you have to fall back on some kind of numerical method, you know? Let me show you one which does have not an odd factor. So I'll make this one a little bit easier for us. I'll factor it to start with, okay? So if you wanted to solve x minus 1 squared times x minus 3 divided by x plus 4 cubed, all right, greater than 0. So I already made it easy. It's all factored to start with, right? So you can identify zeros 1, 3, and minus 4, right? Draw my number line. Minus 4 is over here. I've got my 1. I've got my 3. Right? Now the rest of the theorem, signs flip for odd factor, signs stay same for even factors. So like here, 1 is an even factor because I got x minus 1 squared. All right, so it's not gonna flip sign there. In fact, if you just stop and think about it for a second, x minus 1 squared is irrelevant to the question because x minus 1 squared is what? It's positive, or it could be 0. So you could kind of just ignore it and still solve the problem without that. But let me just put it here and just say it doesn't flip sign. So we'll test 0. What happens when you test 0? Plug in 0, we get 0 minus 1 squared over 0 minus 3, 0 plus 4, which is what? Minus 3 over 4, which is less than 0, right? So my test point of 0 gave me negative. The theorem says, hey, 1 is an even factor. Not going to change sign there. So it stays negative on the other side of 1, right? In contrast, at minus 4, and at 3, we either have just the linear factor x minus 3, or we have it three-peated, triple power here, which means that we're going to go from plus to minus or from minus to plus as we go across those zeros. So we change to plus here, and we change to plus here. The solution, then, minus infinity to minus 4 unioned with 3 to infinity. So I call it the number line technique. I forget what your book calls it. Your book has a name for this thing. I'll tell you in a second here. Well, I saw it before. Well, anyway, we're going to call it the number line technique, if that's all right with you guys. So next time, we'll talk about absolute value. How to solve absolute value equations, how to solve absolute value inequalities. You know, pay close attention in the next lecture. It's really easy if you get it, but so many students kind of just gloss past it and they get half of it wrong when you get to the test. It's always a weakness in test 1 for students in this course. Thanks, guys. Thanks for getting the camera.